Welcome to AI Paper Podcasts. Today we're diving into a really interesting paper from Francois Fleuret over at FAIR, Meta. It's called The Free Transformer, Extending Decoder Transformers with Unsupervised Latent Variables.
Yeah, this one's cool. It basically takes a look at a foundational aspect of models like GPT, the fact that they're purely autoregressive. They just predict the next token, always.
Exactly. And the paper argues that this pure autoregressivity creates a problem. The model has to guess complex things like, is this movie review positive or negative? Or what's the overall structure of this code I'm writing? It has to infer all that implicitly just from the tokens it's already spat out.
Which, as they point out, is computationally heavy. It needs bigger models, and it can be brittle. A few wrong tokens can throw the whole thing off.
So the core solution here, the free transformer idea, is to let the model condition its generation on random latent variables. Let's call them Z. And the really neat part is these Z variables are learned without any supervision using a conditional VAE setup.
And what makes this immediately interesting, I think, is how they built it. It's surprisingly efficient. This Z variable gets injected right into the middle of the decoder stack, like layer L2 plus 1.
Right. And the overhead is tiny. We're talking 3.1% to 3.6% extra compute and memory during training. It's almost nothing for this kind of architectural change.
And the payoff seems pretty significant. They show really substantial improvements on tasks that need reasoning. Think HumanEval Plus for code, MBPP, MMLU. It suggests this tweak improves the model's inductive bias, makes it better at certain kinds of thinking.
Okay, so that's the quick overview. Let's unpack this properly. First off, those limitations of pure autoregressivity.
Yeah, so standard decoders, all they do is estimate the probability of the next token, given all the previous ones. P of Saint plus 1, given S1 to T. That's the whole game.
And the paper uses a great example, movie reviews. If you're training on positive and negative reviews, the model might start generating, the acting was great.
Right, but then it has to figure out, okay, am I now pivoting to say, but the plot was terrible. It never gets to make an explicit internal decision like, okay, planning complete, this will be a negative review overall.
It's all inferred. It has to build that sentiment or structure or whatever implicitly from the token stream itself.
And mathematically, while sure, you can model any distribution autoregressively, the paper argues it gets incredibly complex and inefficient if the real underlying process involves some kind of initial random choice, some latent variable Z.
They use that coin flip analogy, which I think makes it super clear. Imagine you flip a coin, Z. Heads means you generate only A's. Tails means only B's. A simple sequence.
Now, if the model doesn't know Z, if it only sees the sequence A, to predict the next token, it constantly has to re-estimate the probability that the initial hidden coin flip was heads versus tails.
Right, based only on the A's it's seen. And doing that calculation, that internal probability update at every single step, that's the inefficiency.
You end up needing massive model capacity, billions of parameters, just to implicitly track something that could have been decided by one simple coin flip at the start.
Okay, so this complexity leads to the three big drawbacks they list.
Yeah.
First, you said it, unnecessarily complicated computation and needing bigger models just to guess these hidden structures.
Second, fragility. If the model generates a couple of weird tokens early on, maybe an A, then a B, in that coin flip example.
Then its internal estimate of whether it's in an A world or a B world gets totally confused.
Exactly. The whole generation can just go off the rails because those early tokens messed up its implicit understanding.
And the third one?
The third is that these high-level concepts like sentiment or structure or position in their synthetic task, they don't just exist in the model. They have to be constructed kind of after the fact from the tokens.
Which makes the model potentially weak when it encounters stuff slightly outside its training data because it doesn't have a robust, explicit internal handle on the structure it's supposed to be creating.
Yeah. So the whole point of the free transformer is to give the model back that freedom. Let it explicitly condition on some latent random stuff, Z, that isn't directly dictated by the input sequence. Give it an internal planning tool.
Okay, so how do they actually implement this? You mentioned a conditional VAE.
Right, so the abstract idea is when you're generating text at inference time, you first sample a Z from some simple prior distribution, like a standard normal, PZ. Then you run the decoder, but its calculations are influenced or modulated by this sampled Z.
Simple enough at inference, but training sounds harder. You don't have the correct Z for a given training sequence S.
Precisely. So during training, they introduce an encoder. The encoder looks at the real sequence S and tries to predict a good distribution for Z called QZS. Good, meaning a Z that likely would have generated S.
Ah, okay. So the encoder learns to map a real sentence back to a plausible latent plan Z.
Exactly. But there's a catch with VAEs. You have to be careful the encoder doesn't cheat.
Cheat?
Well, if you don't restrict the encoder, it could just learn to copy the entire input sequence S into the latent variable Z. Then the decoder just has to read Z and copy S out. It learns nothing useful for generation time when you don't have S.
Right. That's called posterior collapse, isn't it?
Yep. So you need to limit the information flow from the encoder into Z. And that's done using the Kullback-Leibler divergence, the KL divergence. You add a penalty term to the training loss that measures how different the encoder's output distribution, QZS, is from the simple prior distribution, PZ.
Okay, that forces the encoder to be concise, to only put the most essential structural information into Z, not just copy the whole input.
Exactly. It keeps the decoder honest and ensures Z learns something generally useful.
So that's the VAE theory. Now, the architecture. How did they plug this into a standard decoder without, doubling the model size?
This is where it gets clever. It is basically a standard decoder architecture, but Z gets injected right in the middle at block L2 plus 1, where L is the total number of layers.
Why the middle?
The idea is you let the first half of the decoder, the first L2 blocks, process the input sequence normally, kind of understand the context.
And then you inject Z, this global structural information or plan.
And the second half of the decoder, blocks L2 plus 1 through L, can then use both the process context and this latent variable Z to generate the rest of the sequence.
Okay, that makes sense. And the encoder part, is that heavy?
Surprisingly light. Because they share those first L2 decoder blocks, the encoder essentially takes the output from block L2, passes it through just one extra transformer block. This one's non-causal, specific to the encoder, and then some linear layers produce the parameters for the Z distribution.
So the only extra weights during training are basically one transformer block plus some linear layers.
Pretty much. It's very efficient.
And there was another detail in the paper's diagram figure 2 about the encoder's input. It doesn't use the token embeddings directly for its queries.
Yeah, that's a really smart touch. Instead of feeding the sequence representation token by token into the encoder's attention queries, they use a single learned constant embedding. They call it zeta.
Why do that?
By using one constant query vector, you encourage the encoder's attention mechanism to look globally across the sequence representation coming from the shared blocks. It forces it to summarize the whole sequence into Z rather than just mapping input tokens to latent variables one-to-one.
So it pushes Z to capture more global structural properties like overall sentiment or the plan for a code block.
Exactly. It makes Z more meaningful.
And this efficiency, you mentioned the numbers 3.6% overhead for a 1.5 billion parameter model, 3.1% for an 8 billion. That's actually quite remarkable.
And it really is. It makes it potentially practical to deploy.
Okay, let's talk about Z itself. What does it look like? Is it just one vector?
It's actually a sequence of vectors, Z1 through ZT, one for each token position T. And each ZT is chosen to be a one-hot vector.
One hot over how many dimensions?
This is where it gets wild. They decided to use H16 bits to represent the choice for Z.
16 bits.
Okay.
So the dimension of that one hot vector ZT is 2 to the power of 16.
Which is 65,536, a huge discrete choice space for the latent variable at each token position.
Wow. Why so large?
They mentioned they chose it specifically to be in the same ballpark as typical large language model vocabulary sizes, which are often around, say, 130,000, so it's a comparably complex decision space.
Okay, a 65,000 dimensional latent choice per token. That sounds computationally intense to handle during training.
Yes. And that leads us directly into the training objective and the really crucial component they introduced, the binary mapper.
Right, so the training loss first. It's pretty standard VAE stuff, right?
Basically, yeah. You minimize two things together. The usual cross-entropy loss, which measures how well decoder predicts the next token given the previous ones, and Z.
Plus that KL divergence term we talked about, the penalty that keeps the encoder QZS close to the prior PZ and prevents collapse.
Correct. And to manage that KL term effectively, they use a technique called the free bits method, specifically a token-wise version.
Free bits. What's the intuition there?
Think of it like setting a minimum budget for information. The KL divergence measures how many bits of information Z is encoding about S. The free bits method says, okay, model, you must encode at least, say, kappa bits of information in Z for each token.
So if the KL divergence for a token Z is below that threshold go, The loss function doesn't penalize it. It sort of ignores it.
Exactly. The penalty only kicks in for KL divergence above. If the model is trying to be lazy and encode less than Z, the lack of penalty actually encourages it, or rather, forces it to pack more information into Z until it hits that minimum budget.
Clever. It prevents Z from being ignored if the reconstruction loss part is easy.
Right. Now, the binary mapper. This tackles that 65,536 dimension problem. How does the encoder possibly output parameters for a distribution over 65,536 choices for every single token? Calculating 65,536 logits would be incredibly expensive.
Yeah, that sounds like a non-starter. So how do they get around it?
Instead of outputting 65,536 logits, the encoder outputs just H16 logits per token, much more manageable.
Okay, 16 numbers. How do you get from 16 numbers to a choice out of 65,536?
They treat those 16 logits as representing 16 independent coin flips, or bits. The binary mapper takes each logit, passes it through a sigmoid function to get a probability between 0 and 1, for that bit being 1.
So now you have 16 probabilities. You can sample 16 bits independently, right? Like 0, 1, 1, 0, etc.
Precisely. That gives you an H-bit binary vector, and then they simply use standard binary encoding to map that H-bit vector like 0, 1, 0 into a single integer index between 0 and 2H1, which is 0 to 65,535.
And that integer index tells you which dimension of the 65,536 dimensional one-hot vector state C should be 1.
That's the trick. You get this massive discrete choice space, but generated from only 16 independent probabilistic decisions. It's computationally feasible.
And does this mess up the training, like getting gradients back through that binary sampling and encoding step?
Surprisingly, no. They point out that because the sigmoid function used for the bit probabilities is monotonic, gradients can flow back through the system effectively using techniques like the Gumbel softmax trick or just straight through estimators. It allows end-to-end training of the whole VAE setup.
Okay, that binary mapper seems pretty key to making this whole thing work without blowing up the computation. Very neat.
Definitely. It's a core piece of the puzzle.
All right, so the mechanism seems plausible, efficient, but does it actually work? Let's get into the results.
They started, quite smartly, with a synthetic task just to see what Z was learning. The task was simple: generate a specific target letter, repeated 8 times, at a random position within a sequence, surrounded by noise characters.
So it requires the model to kind of plan, okay, I need to put 8 X's starting at position 15.
Exactly. And they varied that free bits threshold, kappa. What they found was really telling.
What happened?
At very low kappa, the model basically ignored Z and behaved like a standard transformer, struggling with the task. But as they increased kappa, forcing Z to encode more information.
Let me guess. Z started encoding the position.
Bingo. Z explicitly learned to represent the target position of that 8-letter sequence. The model was using the latent variable for planning.
That's cool. Did you learn anything else?
Yeah, as they pushed kappa even higher, Z started encoding information about the noise pattern too, not just the target position. It was capturing more and more of the sequence's underlying structure.
Was there a limit? Could kappa be too high?
Yes. If they set kappa too high, like 4 log 2 in their experiment, the cross-entropy loss collapsed. The encoder basically found a way to stuff all the information about the target tokens into Z, making the decoder's job trivial during training but useless during generation. That KL penalty is crucial.
Okay, so the synthetic task confirms Z can learn meaningful structure. What about real benchmarks?
For the main benchmarks, they were careful to compare against strong, optimized baselines. Models using all the modern bells and whistles, SWG-LU activations, RMS norm, rotary positional embeddings, ROPE, grouped query attention, GQA.
So it wasn't just beating up on a strawman baseline.
No, definitely not. And the results, especially on the smaller 1.5 billion parameter models trained on, I think it was around 47 billion tokens, were pretty striking.
Where do they see the biggest improvements?
Primarily on tasks that require that kind of internal reasoning or structural planning we've been talking about. HumanEval Plus and MBPP really stand out.
Those are the code generation tasks, right?
Yeah.
Generate Python code from a description.
Exactly. Highly structured, requires planning. For the 1-bit free bit setting, capilux 2, HumanEval Plus accuracy jumped by over 55%. MBPP was up nearly 36%.
Wow, 55% relative improvement. That's huge.
It is. And GSM-8Pay, which is solving grade school math word problems, another task needing multi-step reasoning, saw a boost of over 30%.
Okay, that's compelling evidence that Z is helping with reasoning and planning. How about the bigger models?
The 8 billion parameter models trained on 200 billion tokens also showed gains, although maybe not quite as dramatic percentages. CSQA, which is a common sense reasoning benchmark, was up over 26%.
And AMLU. That's a big multitask benchmark.
MMLU saw a solid jump too, nearly 11% improvement. Again, suggesting a broad benefit, but perhaps most pronounced where that explicit latent structure helps most.
Were there tasks where it didn't help much?
Yeah, it seemed less impactful on tasks that are more about straightforward knowledge recall or basic language modeling perplexity. The benefit really shines when the task demands some kind of internal, structured decision-making.
Okay, and they scaled this even further, right, to 1 trillion tokens.
They did. They trained 8 billion parameter models on 1 trillion tokens using a half-bit setting. Kappa it gets log 2 too. This is getting closer to production-scale training runs.
And did the improvements hold up at that scale?
Yes, they did. HumanEval Plus was still up over 11%, MMLU up by 5.2%, CSQA up almost 5.8%. So the benefit seems robust even at massive scale.
It's not just some artifact of smaller data or models.
Seems not. And it's worth briefly mentioning how this differs from older attempts to combine VAEs and transformers like Optimus or AdaV. Those often focused on using VAEs in encoder-decoder setups or required supervision for the latent variable, like predicting a document title. The free transformer is distinct because it's a direct, minimal extension of a decoder-only model, and the latent learning is entirely unsupervised.
Got it. So pulling it all together, what's the big takeaway here?
I think the core message is that adding even a simple, unsupervised latent variable mechanism implemented efficiently like this can significantly improve the inductive bias of standard decoder transformers. It makes them inherently better at tasks involving reasoning, planning, and generating structured outputs.
And the paper connects this to chain of thought prompting, right?
Yeah. They have this intriguing line suggesting that the free transformer aims to do in the latent space with an autoencoder what models using chain of thought do in the token space.
So it's like an implicit hidden chain of thought mechanism.
Sort of, yeah. Or at least it's providing some of that structured planning capability internally rather than forcing the model to write out its reasoning steps explicitly as tokens.
That definitely sounds like a promising direction. Maybe combining both latent planning and explicit token-based reasoning.
Could be very powerful. Looking ahead, the paper does mention that the training wasn't perfectly stable. The performance curves had some bumps.
Right, so future work probably involves finding better optimization techniques for this kind of coupled encoder-decoder system within a decoder.
Exactly. Fine-tuning the training process, maybe exploring different ways to inject Z, and of course scaling it up even further to see how far this approach can go.
Okay, fascinating stuff. So let's leave our listeners with a final thought to chew on.
All right.
If just adding this single latent decision point per token, Z, with only about 3% overhead, gives these kinds of boosts on reasoning tasks, what could we unlock if we designed architectures that allowed for, say, a chain of these latent decisions?
Like an internal multi-step planning process happening entirely in the latent space before generation continues.
Exactly. Instead of forcing all the complex logic and planning into this sequential token stream, what if we built models with dedicated hidden layers for multi-step reasoning and refinement using these kinds of latent variables? What new capabilities might emerge then?
That's a really interesting question. Moving beyond just one Z per step to a sequence of internal latent states. Yeah, definitely something to think about for future architectures.
Food for thought. Thanks for breaking down the free transformer with us today.
My pleasure. It's a neat paper.